Hi, I'm Eldon, and I'm going to present our work Spectral Graphormer, presented at ICCV 2023. 3D hand-pose estimation is a fundamental problem in various downstream applications including AR and VR. Many approaches have already been proposed for hand-pose estimations for either RGB images or depth images. Although they perform well on complex configurations under single-view settings, their dependence on root zone alignment do not provide absolute root pose recovery when applied to multi-view scenarios. Also, they have limited mesh resolutions per hand. Nowadays, many immersive AR/VR applications require accurate estimations of two hands, including extended forearm, at least allow for more realistic and accurate representations of hand movement and gestures. By including the forearm, the orientations and movement of the hand in relation to the arm can provide important contextual information for the user's actions in the virtual environment. Additionally, it can reduce error and improve the stability of the tracking system, which is important for maintaining immersion and avoiding disorientations in AR/VR applications. Therefore, in this work, we consider a challenging problem setting where we jointly reconstruct two hand meshes with forearm from multi-view RGB images. The input images are rendered into egocentric view to mimic AR/VR scenarios. However, as in many other areas of computer vision, there is currently no suitable dataset for a typically supervised deep learning setup. Therefore, it is not suitable to validate our approach, and we are motivated to create a large-scale egocentric synthetic dataset with improved environment and lighting variations. As manually annotating 3D hand meshes on real data is extremely laborious and expensive, we first create a large-scale synthetic multi-view dataset containing realistic hand motions from egocentric camera viewpoints rendered under large variations of background and illumination. Extending the current state-of-the-art metro model from single-view to multi-view setting is non-trivial. The first reason is that the current method have overlooked the importance of efficient token design as they concatenate redundant global features to each of the tokens, and this requires a large number of learnable parameters when extending to multi-view settings. In this paper, we incorporate the properties of graph Laplacian from the spectral graph theory into the design of our transformer-based network architecture. There are two problems in the original metro. First, global image features are concatenated in an overly duplicated way. Second, the pooling operations on image features would lose spatial information, which is proven to be useful in multi-view settings. Here we propose a simple soft attention fusion strategy, which is coupled with mesh segmentations with spectral clustering. Here we can interpret the eigenvectors of the graph Laplacian as the generalized concept of sinusoidal functions of positional encoding in transformers. We found that simply relying on fully connected layers to upsample meshes to target resolution is insufficient, as this process introduces instability and disruption to the mesh, even with mesh regularization loss terms. Therefore, we propose to couple fully connected layers with spatial filtering in our decoder. Here we can interpret from a signal processing perspective, where the Laplacian eigenvectors define signals that vary smoothly across the graph, with the smoothest signals indicating the coarse community structure of the mesh. We found that the resulting meshes can sometimes be physically implausible. To avoid penetrations, we extend repulsion loss into an optimization-based strategy which does not require any form of precomputation and is more generalizable to other meshes. We minimize this collision loss with as rigid as possible regularizations on the mesh shape. We achieve a very small hand error which is able to reconstruct meshes at high details. With the lightweight soft attention fusion strategies, we are able to reduce the number of parameters by 35%. We further reduce the number of parameters with graph decoder. We show that relying on fully connected layers to upsample meshes is inadequate for high-resolution mesh reconstruction. In contrast, our spectral graph decoder can accurately capture detailed surface features like nails. Our model shows robustness to various extreme self-occlusions, lighting conditions, and scene. Fine mesh reconstruction details are well preserved in all scenarios. Additional qualitative examples of mesh refinement at inference. Our optimization-based strategy shows robustness to various hand poses. Although our methods result in accurate and physically plausible two-hand reconstructions, the results are sometimes not plausible when self-penetration is highly complex. We believe this problem can be tackled in the future by incorporating temporal information and more advanced physical modeling into our proposed framework. To verify our multi-view fusion approach, we collect real data from multi-view stereo system. The results show that the two baselines tend to overfit to the camera configurations. We provide qualitative examples on our real hand-proof dataset. We found that we can reduce the model size by 3 times while maintaining metro baseline performance. We provide additional qualitative examples from our synthetic dataset. Thank you for listening.